All right, let's get into it. Today, we're basically going to become language architects. We're going to look at programming languages not just as tools we use, but as these really complex structures, designed with actual blueprints and built from the ground up. So if you're a computer science student, you are swimming in an absolute sea of languages, right? C++, Java, Python, the list goes on. But have you ever really stopped and asked why? Why are there so many, and what really makes them different under the hood? It's not just about semicolons. There are fundamental architectural decisions that make Python feel totally different from C++, and that's exactly what we're going to deconstruct today. So here's our game plan. First, we're going to look at the blueprints, the basic rules of any language. Then we'll check out the core building materials. After that, we'll see how designers use some clever tricks to hide complexity before we walk through a real-world example, Python, to see it all in action. And finally, we'll wrap up with the key takeaways for your own mental toolkit. Every great building starts with a blueprint. In the world of programming, our blueprints are all about two huge concepts: syntax and semantics. These are the absolute non-negotiable fundamentals that dictate every single line of code you will ever write. Okay, first up, syntax. The easiest way to think about this is just grammar. It's the set of strict rules for how you have to arrange your words and symbols. Where the parentheses go, how you declare a variable. If you get the syntax wrong, the compiler or interpreter just throws its hands up. It has no idea what you're even trying to say. But just because your sentence is grammatically correct doesn't mean it makes any sense, right? That's where semantics comes in. Semantics is all about the meaning. Once you've written something that's syntactically valid, semantics is what defines what those instructions actually tell the computer to do. It's the logic. And this slide just nails the difference. Look at the code on the left. The grammar is perfect. It's syntactically correct. But the meaning, the semantics, is completely broken. You're defining a constant and then immediately trying to change it. That makes no logical sense. It's a semantic error. Now, the code on the right, that's just a mess from the start. The grammar is all wrong, so it's syntactically incorrect. We don't even get a chance to worry about what it means. All right, so we've got our blueprints. Now it's time to look at the actual building materials. These are the absolute core units of any program: the values, the types they belong to, the variables we store them in, and the bindings that tie it all together. So every single piece of information in a program is a value, and every single value has a data type. Just think of the data type as the specifications for your materials. It tells the computer, hey, this is a whole number, or this is a piece of text. It defines how much memory it needs and what kinds of things you can do with it. And here are some of those really basic building blocks. You've got your int for whole numbers, float for numbers with decimals, and char for single characters. They might look simple, but these are literally the bricks and mortar of programming. Every single complex thing you build, from a social media profile to a video game character, is at its core built from these simple primitive types. So where do we put these values? We store them in variables. Now here's a key idea. A variable isn't just a random name. It's actually a stand-in, an abstraction, for a physical spot in your computer's memory. This is all thanks to the von Neumann architecture, which is the basic design for almost all modern computers, where our code and our data live together in memory. That's what lets us put a convenient name on a memory address and use it to store our stuff. So what's the magic that connects a variable's name to its type, its memory location, and its actual value? That whole process is called binding. Binding is the glue. It's the act of creating these links. And as you're about to see, when this binding happens, whether it's when you compile the code or when you run it, is a huge architectural choice that changes everything. As our programs get bigger, they get way more complex. A smart architect doesn't build a skyscraper brick by brick, right? They use prefabricated sections. In programming, we do the same thing, and our most powerful tool for it is called abstraction. Abstraction is basically the art of hiding the messy details. It lets us work with really complex things by focusing only on what they do, not how they do it. It is, without a doubt, the single most important technique we have for managing the insane complexity of modern software. And the most common form of this is something you already do all the time: functions. We call this procedural abstraction. The idea is simple, right? You find a task you need to do over and over, you wrap up all the logic inside a function, and you give it a name. From that point on, you just call the name. You don't have to care about the complicated steps happening inside. It's like pressing a button on a coffee machine. You just want coffee, you don't need to know how it grinds the beans. Then we have the next level, data abstraction. This is even cooler. Here, we don't just hide the actions, we bundle the data itself together with the specific functions that are allowed to touch that data. This creates a neat little package, a self-contained unit. It protects the data, keeps things organized, and it's really the core idea that leads to object-oriented programming. Okay, that's enough theory. Let's get our hands dirty and look at a real building, the Python language. We're going to see how the architects of Python took all these principles, syntax, variables, abstraction, and put them into practice to create the language we know. So the whole philosophy behind Python is about something called pragmatics. Basically, designing a language that's easy and pleasant for humans to write and, just as importantly, to read. The designers intentionally chose to prioritize flexibility and what we call writability over raw maximum performance. That's a huge architectural decision. And you can see this choice right here. Look how we create the student ID variable. We just give it a name and a value. Notice what's missing. We didn't have to say int student ID. Why not? Because in Python, the type isn't bound to the name. It's bound to the value. The number 95 is an integer, period. The name student ID is just a label we're currently pointing at it. This is called dynamic typing, and it means all that type binding happens when the code is actually running. And check out how flexible this is. On the very next line, you can take that exact same name, student ID, and just point it at something completely different, like a string. The name is just a label, and Python makes it incredibly easy to peel that label off one value and stick it onto another one, even if it's a totally different type. And of course, this focus on readability makes abstraction in Python feel completely natural. You can define a function like calculate_grade and hide all the messy logic for how grades are actually determined inside it. Anyone using your function just needs to know one thing. Give it a score, get a grade back. The details are hidden. That's that clean architectural philosophy in practice. So we finished our tour. What are the key architectural blueprints that every programmer should have in their back pocket when they're looking at a new language? Here's the toolkit you need. First, always separate syntax, the rules, from semantics, the meaning. Second, remember that variables are just names for spots in memory, and binding is the glue. Third, abstraction is your best friend for fighting complexity. And finally, and this is maybe the most important one, realize that every feature in a programming language is a design trade-off. It's always a balancing act between things like how easy it is to write, how safe it is to run, and how fast it performs. And that brings us to one last question to chew on. Python is amazingly easy to write, right? It offers incredible writability. But what's the trade-off? By waiting until the program is running to check types, what kind of errors might pop up that a stricter language would have caught before you even ran the code? In other words, what is the hidden cost of all that wonderful simplicity? Something for you to think about. Thanks for joining me.